So we would like to kick off our presentation by posing a question. How many of you woke up this morning, drank a cup of coffee? Maybe every morning. You know, you need that caffeine. Great, a lot of you. You know, wake up, keep it going throughout the day. But now, how many of you also just drink coffee because you like the taste? And so maybe you enjoy a cup after dinner, right before you go to sleep. For that, you're likely going to turn to decaf coffee. And if you've ever wondered how coffee gets into that decaffeinated state, you can thank a chemical called ethyl acetate. My name is Carrie Huser, and I'm here with my team members, Neha Narain and Vincent Lau, and we're representing a startup company called Ethylend. Ethylend is a company that's focusing on creating a new generation of green chemicals. Our first one, which we're going to be talking about today, is indeed ethyl acetate. So what is ethyl acetate? It's a specialty chemical that has a market purity requirement of 99.8% and a consumption of over 2 million tons per year. That is set to grow at a compound annual growth rate of 5.75% between this year and 2023. So what is it used for? As I hinted, it's largely used in the decaffeination processes of coffee, tea leaves, and cocoa. It's also very commonly used as a solvent. So if you've changed the color of your house, ethyl acetate is in that paint. And if you put perfume on this morning, there's ethyl acetate in there as well. So while we understand that chemicals are maybe not as flashy as AI, machine learning, all of those kind of startups, it is very important and it will impact your daily life. In addition, the main importance of our company comes from this aspect of sustainability. So traditionally, well-established companies in the ethyl acetate market will use what's called the Fischer esterification reaction. This uses kind of natural gases and fossil fuels to derive their feedstocks. This makes this extremely unsustainable. And so large companies like Ineos and Celanese that are the main producer of ethyl acetate today make billions off this unsustainable process. Our company has the goal of creating that same specialty chemical in a much more sustainable way. And to talk about how we do that, my partner Vincent Lau is going to tell you.
Thank you, Carrie. More specifically, we're looking to turn this piece of corn into ethyl acetate, which will then become your consumer products, such as this bottle of perfume that you guys use on a daily basis. However, to be more specific, we aren't actually directly turning corn into ethyl acetate. We're actually looking to turn fermentation-based ethanol, which comes from corn, into ethyl acetate. So instead of reinventing the wheel, we're actually going to source ethanol directly from some corn to ethanol plant, which actually fuels 10% of the gasoline that's in the cars that you guys use to drive here today. So how exactly do we do this process? Well, unfortunately, we can't really build the plant. We don't really have the capital to build it and to show off what this plant will do. So instead, what we'll do is we'll show you the main process flow diagram of how we're going to turn ethanol into ethyl acetate. Our flow diagram is broken down into 3 main segments. Highlighted in the red is going to be the main blocks that are basically doing all the heavy lifting in each segment. In this first block, which is a reactive distillation column, all the chemistry occurs. In our next segment, a hydrogenation reactor, this essentially helps us convert byproducts into something that's easier to separate. And finally, our distillation column performs our final separation. To go into more detail, we utilize reactive distillation to produce ethyl acetate efficiently. Traditionally, in chemical engineering and chemical productions, products are typically produced first in a reactor, followed by a separator to separate out our desired from our undesirable products. We'll be using a process known as process intensification to combine these 2 processes into one thing known as reactive distillation. Shown here is the chemistry that's occurring, which produces hydrogen as a co-product in the vapor distillate of this distillation column and ethyl acetate as a bottoms product. We've added a stripping column in order to recover some of the intermediate products that are lost in this process to increase both efficiency in terms of money as well as time. This entire process first starts by pressurizing the feed to 20 atmospheres. Next, we'll be using a hydrogenation reactor to make those byproducts that are produced in this process a bit easier to deal with. To put this into perspective, if we didn't have this hydrogenation reactor, we would require a distillation column, just like the ones you guys see on your way to the airport, that is 40 stories high. As you can see, that's probably not exactly economical to build. First, to deal with the first byproduct in our process, which is water, we'll be using a molecular sieve. Then, our hydrogenation reactor will convert the byproducts that I mentioned previously into things that are a bit easier to separate in a future process. The reason why we require such a large distillation column is because that the differences in the boiling points between ethyl acetate as well as these other byproducts aren't really there. By converting these to other elements and other compounds, the boiling point differences will be a lot higher, so we can actually boil off our ethyl acetate in our final segment. Finally, after this reactor, we'll be using a flash heat exchanger, which essentially will remove all the hydrogen that we're using in the hydrogenation reactor. Then, finally, in our last segment, we'll be separating out all of our ethyl acetate using a distillation column. Just to put this into perspective, instead of the 40-story high tower that we needed before, we're only going to need a much more conservative 5-story tower, which is pretty common within the chemical industry. This essentially will take all the effluent out of our previous hydrogenation reactor and form ethyl acetate as a vapor distillate. All of our byproducts will end up as a liquid in the bottom, and we will go into a storage unit. As I mentioned before, there's still some hydrogen present, so we're going to have a vent that essentially will remove all of that to give us a desired 99.8% purity that you guys can use in all of your consumer products.
Thank you, Vincent. So Vincent just gave you a really good overview of the technical standpoint of our process, and I'm going to go into some of the total capital investment required. As Vincent mentioned, unfortunately, we did not have $16.9 million to build our process, so we showed you the process flow diagram. We need a working capital of $2.2 million and a total permanent investment of $14.7 million. Off that 14.7, $10.1 million is our total bare module equipment cost, which typically is the most expensive unit in any process. So we see a profitable venture yielding strong economic metrics. As you can see here, we break even 4 years from today or 2 years into production, as it takes 1 year to construct our plant. We have a total net present value of $23.8 million if we project the life of our plant to be 15 years, which is typical in the chemical industry. And we have an IRR of 38.4% and an ROI of 43.2%, all signaling strong measures of profitability. Unfortunately, we don't have enough time to show you some of the sensitivity analyses we ran, but this is a pretty robust and conservative approach to measuring the profitability. We also note that Ethylend would be in strong financial health if we were to go through with this process, as we have a working capital ratio of 2.38, which means we have enough short-term liquidity to pay off our debt. So, as Carrie mentioned, our ethyl acetate is sustainable. Think about the time when you went to Trader Joe's and bought organic and inorganic strawberries. The inorganic strawberries sold for $3.99, and the organic strawberries sold for $5.99. Maybe you reach for the organic strawberries, and that price difference is the green premium I'm talking about here. Our sustainable ethyl acetate is able to yield a green premium. The base case economic analysis I showed you did not have a green premium on our product. However, don't take my word for it. The Nova Institute in Germany ran a study of bio-based chemical products and saw that these products are able to yield a green premium of 10 to 20%. So although we don't need this green premium on our ethyl acetate to compete in a profitable way, we do require it as a safety net. As you all know, commodity chemicals are exposed to a great amount of commodity pricing, such as market shocks in the ethanol and ethyl acetate pricing. I'm going to conclude by saying Ethylend aims to provide the world with a suite of sustainable produced chemicals, and we begin with ethyl acetate. We're able to use a novel and an innovative approach used in chemical engineering, such as reactive distillation, and we hope that the green premium would be able to allow a safety net to compete against the large chemical giants such as Ineos and Celanese. Today, I hope you can see that the move to sustainability is very, very important, such as other industries have moved towards sustainably produced energy in the chemical engineering scheme. Before we go into questions, we have a quick disclaimer. There is a real-world startup called GreenYug. GreenYug had made wild claims that this process was profitable from a technical and economic standpoint, and we just couldn't believe it. So what we've produced here is Ethylend, a startup, but we really reverse engineered their process to see whether it would be feasible. And our conclusion is that GreenYug is a credible threat. This sustainable approach is happening in the chemical industry and is definitely something you need to take note of. Thank you so much, and we'll start off with questions.
You looked
Definitely. So we obviously as a startup would have to start we aimed for our plant to produce 50 kilotons a year. Celanese and INEOS make up the majority of production. Actually, the majority of production globally happens in China and in Asia. They hold the market dominant. However, in the US, this would definitely be competitive on a capacity scale. Given that it's sustainable, we have to compete against ethyl acetate markets, but we're creating our own market and creating a sustainable approach. So we may begin by having to compete against them, but we do see customer adoption towards the sustainability angle.
So where do you plan on putting your facility?
Absolutely.
So our facility, like I mentioned before, utilizes fermentation-based ethanol. So our goal is to actually locate the facility near or approximately near corn to ethanol plants in sort of the Midwest of the United States.
So did you take into account for your cost estimate the cost of transporting your feedstock to your facility and the access of feedstock to the facility?
So absolutely. So when we did our base case economic analysis, we assumed that we were located to an ADM corn plant, which is located in Columbus, Nebraska. So in our base case economic analysis, we did not assume a discount on the ethanol feedstock, which you may probably see if you were located. Given that you're close to a corn to ADM corn plant, you have a pipeline that gets it directly through to us. That $10.1 million total bare module cost that I mentioned is inclusive of that short, minimal cost that it would take to pipe over the ethanol feedstock.
One last question.
Yeah.
Do you consider switchgrass as an option instead of corn?
So we didn't look specifically about how the ethanol would be created, but mainly we would just directly purchase something that another company has already produced. So we aren't trying to reinvent the wheel by turning some sort of biomass into ethanol.
Good.
Thank you.
Are there any air releases to the environment during the process itself that would require a Clean Air Act permit or something like that? Often that's something you have to consider for toxicity and an economic standpoint.
So the only vapor and gaseous streams that we produce in our process is mainly hydrogen gas. And to deal with that, we're essentially going to combust it and use it for its fuel value. We looked into trying to sell hydrogen gas, even though it isn't exactly a commodity chemical that there is an established market for. But we found out that even if there was a buyer, our purity isn't high enough, and the cost to actually get it to something that another customer would want is going to be far too expensive. So essentially, we're going to use it as heating value to minimize the amount of utilities that we need to purchase to run this operation.
What were your real estate cost assumptions in the model in terms of acreage and/or rent or purchase?
So we assumed that the total land cost was 2.2% of depreciable capital. That was kind of the assumption we made there. Our cost of land is included in that $14.7 million. Yes.
Yeah, I'm just curious, the chemistry, how did you determine that was feasible? Has it been done, or?
Absolutely.
Sure. So if we go back to the chemical reactions that are actually happening, this was actually developed at university labs, and they've actually done lab scale experiments in which utilize this two-step reaction to convert our ethanol to ethyl acetate. So simply what we're doing here is we're using some research data, such as kinetics, from these lab scale studies in order to scale it up to something that is obviously more applicable to somebody like us, where we want to produce a large amount of this chemical.
Are you assuming similar yields and purities and things?
So we,
Or were you scaling that up?
So yes, so that was one of the most difficult parts of our project. We were given sort of kinetic data, so basically mathematical models that tell us, in given conditions, how much product should we produce and at what rates. And using that, we were able to create our model to model the actual reactive distillation.
Also add that the Greenyug patents, as I mentioned, Greenyug is present. They had a lab scale data of the reactive distillation column. So as Vincent mentioned, utilizing all of those mathematical and kinetic models, we were able to scale up. So we did have a understanding of operating conditions, of the number of trays, and unfortunately, we didn't have enough time to go into that, but happy to speak about it as well.
Yes.
So from a competitive lens, a lot of companies are moving towards pollutants and ingredients. Have you thought about what other chemicals would you consider? And then have you also thought about, rather than building your own plant, partnering with, say, EDM, which is a fairly large global producer, and using some of your technology within their plants?
Absolutely. So we did think about that. We didn't explicitly, it wasn't beyond the scope of our project to go to another specialty chemical, but what would happen is because we're using an entirely different column, such as a reactive distillation column, it may or may not be a little difficult to insert that into an existing plant.
You could approach it, you can approach these companies and say you have technology.
Absolutely, and as I'm sure you're aware, a lot of these large chemical companies acquire these startups with innovative processes, so that's pretty typical in the chemical industry. So we would position ourselves that we would perhaps be acquired in a few years.
Or you could get funding from the media.
Yeah, absolutely.
Thank you very much.
Thank you.
Thank you.